Okay, we will continue with lecture, and now will be about power budget radar equation. On first formula you can see reflected wave-free surface power density. S2 it is received signal, S1 is transmitted signal, RCS is radar cross section. It is something in meter square what is like effective reflection surface of transmitted wave from the surface, from the target, something like this. Later you will see exact formula. Surface power density at the radar antenna is defined by second formula, and after some mathematical changes we could make received power at antenna output or input. It is same antenna, so it is received power of antenna. So you can see that received power in radar depends on many variables. You can see it is transmitting power, gain of transmitting antenna, gain of receiver antenna. Of course, if you use same antenna, GT and GR is same because it is same antenna. Then you have small t square, small r square. It is parameter related to antenna. F up to 4, it is parameter related to antenna pattern. How is designed antenna pattern? But usually this capital F4 we can ignore it and tell it that is 1. It is depends in some small thing. Then is RCS, then is lambda squared, and lambda squared of course it is related to carrier frequency. And what is interesting in denominator is 4p up to 3, R up to 4, and capital L squared. And what is this? It is losses. It is a lot of different kind of losses. You can have atmospheric loss, loss of polarization, loss of free space, and I can continue so on. So generally what is for us important, this is transmitted power. Okay, it is clear message. Like transmitted power in previous example was 14 kilowatts. Okay, pulse. It is transmitter antenna gain, maybe 20, 34, 40 decibels, something like this. If we use same antenna, it is same numbers, of course. This is antenna thing. I will skip it because we don't have time. RCS. So it is generally area of surface of my reflected surface. So it is important. If this will be really small drone, of course it will be receiver power will be lower, and this we can't influence so much because it is carrier frequency. So if you decide that your radar works in 10 gigahertz, it is for you just constant. This is problem, because imagine 1 kilometer, 1000 up to 4, it is a huge number. Up to 80 kilometers, 80,000 up to 4, oh, it is very huge number. And imagine some radar types where its range 450, 500 kilometers. Can you imagine this number? Very high. So what is main message? This is a really small number, you can imagine. And what is interestingness, this is related with signal to noise ratio, because it is clear if my received signal will be lower, the influence of noise will be higher. Clear. So I need this ratio best one. So what is mean? I want strong signal and low noise. This is Boltzmann constant. it is temperature of system, and it is my bandwidth, and it is related to my transmitter pulse. So it is radar equation. Of course, we usually don't compute receive power in this form, but we may convert it to decibels. Why? Multiplication is just summation and division is just with minds. It is much better. There you have example. So if you can see this example, for I just try put example, ratio between transmitting and receiving power, it is about 200 decibels. So if you make inversion 200 decibels, and you know that 3 decibels is to half power in linear units. So 200, it is very low number. I'm sorry, I have so many slides that about 2-3 slides I need to skip it. There is an example of received signals level from precision approach radar. So you can see transmitter power is about 100 kilowatts. And in second row you have units in dB, because like radar engineers we work more in dB than in classic units. Because why? Because difference between transmitter power and receiver power is so big numbers that these numbers will be huge, extremely big or extremely slow. So dB is much more better for us. Antenna gain, how I say, about 40 dB. Antenna radiation pattern maxima, if it is 1. Form factor, it is 1. Wavelength, it is 3 centimeters. Radar cross section, evaluation 1 square meter. Range 20 kilometer. And received power, if you will make sum of all this, you will see minus 74 dB. It is just example. Of course, for another radar will have another values. But if you are planning, like a radar system engineer, which power do you need? You always need compute something like this, some like equation. Okay, I skip it. Then I will talk about range equation, because I already told you briefly. Okay, range equation. What is mean range equation? It is not mean, okay, my radar has range 100 kilometers. It is not sufficient information. Under which condition has range 100 kilometer? And of course, we just make derivation of this, and it is received power must be higher than some minimal power. What is minimal power? If minimal power is power that if will be my receiver signal under minimal power, my signal will be lost in noise. I can't recognize, I can't detect, I can't process, I can't do it anything else. So I think that is clear. And of course it is received power, so I will use previous power budget equation, and this minimal is signal to noise ratio minimum value. So what is mean? It is minimal value of signals to noise that allow me detection of target generally. And this is multiplication by power of noise, and power of noise is computed by Boltzmann constant multiplied by temperature of system multiplied by bandwidth of noise. Because imagine if I have 1 megahertz and some amount of noise, if I will extend it to 2 megahertz, noise will be doubled. Why? Because it's doubled bandwidth. It is independent. So there, don't think that if you will do it narrower bandwidth that you will make limitation of noise. Yes, you will limit, but you will limit also your bandwidth. So there is no win-win situation about noise. Noise is always present and always will be in wall bandwidth. So if I will compute signal to noise ratio, what is minimum, so it is mean how weak could be signal to still make a detection. It is something like this, and it is with pulse compression, without pulse compression and with pulse compression. So you need to satisfy also this condition. So when we talk about ambiguity range that depends on PRI and so on, it was theoretical value. Why? Because it depends only on PRI, but I didn't consider power budget. So it is mean, okay, theoretically I can have it range 100 kilometer, but it is not true. It will be much lower because I don't add to this ambiguity range. I didn't consider power budget equation. So, and there is some derivation of this equation, and in the maximum of antenna diagram pattern is maximum with considering all things of power is divided by this equation. You need just follow and put all these inputs. I am sorry, I need to little speed up this, but you can just use it. It is in classic any radar signal book, you can find this equation. Now I want to say a few words about reflective properties of targets. So imagine we have impacting wave and what on which depend impacting wave. We can have it monostatic or bistatic reflection. I will talk only about monostatic. There is important properties, polarization, and how you know we can have three different kind polarization: vertical, horizontal, and cross polarization. That you transmit one polarization and receive another polarization. It is important because when I presenting results from our measurement, I always have vertical, horizontal, and cross polarization. I will show you later that cross polarization almost hidden any reflection from wind turbine. That is not good that we use vertical or horizontal. What is radar cross section? Imagine that is some surface, plane, drone, anything what you can imagine, and reflectex wave. It is square meter and it is angle, and it is depends on all this. So it is, you can see it is depends on angle, because of course if I have this object, my reflection, it depends on angle on any surface, and it is very variable. How looks real radar cross section? Okay, it is on this slide. This is example of radar cross section for one cut. Of course this is azimuth, and you can see that is very variable. Why? Because plane is complicated. It is reflection from individual parts, and everything is influenced by shape of this target when it's reflected. And what could be values of this RCS, I will come back. Usually RCS, they told you, okay, small aircraft, they have on band 1, 2, 3, 5, 10, 17 gigahertz and so on, they have results of RCS, radar cross section. So it is 2 square meter, 3, 2.5, 5 to 8, and so on and so on. But can you see this result? It is one number. And check reality. Okay, 5 square meters. but it is in average. It does not mean that is true. So definition RCS by one single number is not good, because this is reality. Oh, sorry. This is yes. This is some average approximation. Okay, you can say, okay, this object has about 2 square meters. Yes, but in some direction could have 5, in some direction almost 0, because it is dependent on azimuth, on shape of target. So please, this is a nice example, but this is so far away from reality. It is some average description by numbers. But you see in previous slide, it is very complicated. You even can't compute, you can just measure. For measuring of RCS, if you want to measure like some UAVs or some targets, antenna, what do you want? You need an anechoic chamber, of course. Why? Because I need to remove any influence of signal that is in environment. I need just a reflection from this one. I don't know, do you have on IIT an anechoic chamber, some big one? Yeah, you have it. We also have it up to 40 gigahertz. So it is like 4 by 5 meters, something like this. So we can measure relatively big UAVs or antenna design pattern, of course, and so on and so on. So check about illustrative figures of RCN in square meters. Insect, birds, it is about 94 dB. Some small plane minus 10, people, and so on and so on. And check this. This reflection could hidden and all of this. Okay, wind turbines didn't hidden racket, but we probably will have problem with this object. So it is clear message that wind turbines is really bad for us, because reflection surface is a really big one. And it is 1.5 megawatts. Now I present you that we have bigger one, about 6 up to 8 megawatts. So blade is much huge. So it will be probably go to right. There is some few examples of real radar signal processor, some records. Again, it is from Czech Republic, from Čáslav, and this, maybe it is hardly visible. There is some few lines, colorful. This is clouds, so it was some cloudy. This is reflection from surface. And this is these hills, and again these hills. So you can see this. This is visualization of amplitude, and this is visualization of phase. So you can see why this is black one, because it is static. Why this is not black one, because cloud moving. So it is like this, but there is no target present. There is another example of radar signals where is dark. It is zero Doppler shift, so it is mean static. This blue one, it is departing clouds, and this red one is incoming. Why different color? If something go away from me, Doppler shift will be negative and positive, so it is just different coloring. Okay, now I will go for radar signals. This is my transmitted pulse. Clear. I will not talk about inner modulation. It is just pulse. And this is length of pulse. And there you can see length of pulse plus some amount of time, we call it blind zone. And this is this blind zone that I already present you in this circle. It is zone where after I finish transmission, I can't receive any answer because signal will be so strong that will destroy my receiver. Clear? This is PRI. It is difference between two pulses. It is clear. Inverse value is PRF, pulse repetition frequency. There is instrumented range, and what is mean? It is mean where my radar listening of receiving signal. Why he didn't receive there? We call it dead zone. Why? Because in this dead zone we use it for calibration of radar, we use it for checking of health of radar, for a reconfiguration of pulse. Imagine if this pulse and this pulse will be in some mode, short one, long one, short one, long one, or something like this. I need to switch. So in this time, and I use it for switching and of maintenance, and for all this I use this dead zone. So this is my unambiguity range where I can record my received signal. There is too short, there is too long, if you understand me. So, and of course this is automatically repeated until forever, until you switch down, of course, radar or something like this. So it is like this. So I think that there is no more commentary. So this was already present, but now it is in more detail. So we are switching only to receiver part. And generally after IQ data, when we take samples from analog to digital domain, we are after AD conversion. It first will be pulse compression. Pulse compression is cross correlation, I already talked about it. Then is MTI, MTD filtration, I already talked. Moving target indicator, it is mean removing clutter. Everything what is not moving just go away, because it is reflection from environment and I don't want them in my signal. I don't need them. Of course, if you will make SAR, synthetic aperture radar, so scanning Earth, you are interested only in this, so it is different task. But we will state that we will detect moving target. Then we have MTD, moving target detector. It is bank of filters where each filter detects specific range of velocities. And how looks like? What do you think that will be? Which type of filter from the main four, you know, low pass, high pass, band pass, and all these things? So what do you want? It is band pass filter. Design it for specific Doppler shifts only. It is nothing else. It is not. It could be complicated, of course, this filter, but in generally meaning it is not so bad. Then is detector. And what doing detector? Imagine that I always talk about radar cell. So it is mean radar cell is resolution cell one by one. And it is about detector. Detector told me is in this range, and in Doppler it is present target 0, 1, yes, no. If no, I don't care. If yes, I care what is type, and I move in next operation. So imagine like a grid, divide it, and each cell you just checking it is there, it is not there, it is there, it is not there, it is there, it is not there, and so on. Then is, okay, it was integration, then is detection, and there is CFAR. It is constant false alarm rate. Okay, it sounds honestly, but what is it? It is mean with which probability is in this cell target, because I can set it constant false alarm rate CFAR on constant value, and if amplitude of my received signal in these cells will be higher than threshold, there is target. If it will be under threshold, it is no target. But this will be very influenced by environment, because in some cell could be low reflection, in some high, so we usually don't use this CFAR like constant, but we call it adaptive CFAR, because it is adaptation to your clutter, to your reflection that you don't want in a signal. So it is CFAR. And then is coordinates extractor. What is mean? Extraction coordinates, it is mean, imagine you have mobile and now radar, and first pulse hit this and reflect back to radar, second pulse, third pulse, fourth pulse, and so on. So I have 5 reflection like example, but all correspond to one target, my mobile or UAV or big plane. So I need to make matching of all mutual detection that correspond to one target, because you don't get only one reflection per target, but you will get multiple. On which one depends? On how quickly you send PRI and size of target. And then you need to make some analysis how make the cloud of point reflection to one object. You need to make some decision. Maybe you know DB scan method that take clouds of point reflection put together or something like this. So it is target coordinators. Generally, radar signal and data processing we divide it to 3 parts. Primary, it is pull compression, Doppler filtering, target detection. So their target detection is this target, it is not target. Then secondary processing, it is target tracking. So if I know after extraction, I know coordinates of targets, okay, there is target. I am interested in secondary processing. If this target is moving, where will be after 1 second, 2 seconds, 3 seconds, 4 seconds? So what is target tracking? Just showing where is my target. So it is individual detection, extracted coordinate system that show me on map. And there also is including additional information. So if my target has a ADS-B, I know what is type of target. I know height of target on the ground, and so on and so on. Then we have tertial processing, and it is about data fusion. If you have multiple radars, because imagine if you have multiple radars, distance, speed is relative value. It is only depends. It is only valid to one radar. For second radar will be different distance and different speed, because it is depends on movement of target. So it is clear that you make on some logic fusion and tell him, okay, this target with this range with this speed correspond to this target with different range and different speed. Because why is different these values? Because it is different mutual position between 2 radars and this target. So, and now we will go to range quanta and Doppler sampling. Imagine that this is one PRI, one pulse. But what I will do it after I receive pulse? Sampling. So once, like one PRI, it is sampled. Do you agree? So this is one PRI, this is second PRI, this is third PRI, and so on and so on and so on. Number of PRI that I will integrate together. Okay. If I will take one sample, it is this one. Second, this one, and so on and so on. From second PRI, first sample is this one, and this one, and this one. And what do you need to compute? Spectrum of signal. Do you agree? We are very dependent on spectrum. But how you won't compute spectrum from one sample, if you get my point? It is not possible. From this, it is also one sample. It is not possible. So imagine that there is visualization of what's happened. I will take example 1000 samples from PRI, put it there, 1000, put it there, and so on. Is it clear? Of course, this not happen in reality, because you will continue, you want to compute spectrum. So you will take 1000 PRI, and we call it CPI. It is coherent processal interval. So from one PRI you can't compute spectrum. Why? You have one sample. How will look slow spectrum? One line or just one point? It is nothing. What do you need? You need more samples, of course, to compute spectrum. And it is this, we call it pulse compression. And now imagine I will take samples from first PRI, second, and so on and so on, and make metrics. And then take it. This sample, always first sample for individual PRI. And if it will be 1000, then one CPI is 1000 of PRIs. And make metrics. So this is correspond of first sample of first PRIs, first sample of second PRI, and so on and so on and so on. And then I will always take this column. And how many values will be there? If it's 1000 PRIs, 1000 samples, and can compute by FFT spectrum. And it is called Doppler filtering, and show you spectrum of your this one. This will be spectrum of second samples, and so on and so on. So it is mean this is spectrum in one time instance, second instance, spectrogram. But this not happen in reality, because you will have continuous sample. But always, if you want to compute this spectrum, you need to wait for length of CPI, if you understand me. And I think that for today it was the hardest point. If you get this, it is perfect. Because, or if you have questions, just ask me. And of course, this length is one sampling interval. This we call it fast time. Why fast time? It is very fast. And this we call it slow time. So we have two times, because you always waiting one PRI and one PRI and one PRI for corresponding samples. So please, we have two times slow and fast time. Fast time, samples in PRI. Slow time, spectrum, like this one. And so if CPI will be only 100 samples, how will look your spectrum? Not much good. Why? Because you have only 100 samples, so it will be not so many information. So if you will have higher, longer CPI, you will get better resolution on spectrum. And better resolution, you can easily more separate targets. But yeah. Of course, but please be careful. You need also make a higher level of sampling. So this is little confusing because it is like sampling in time and number of CPI. It is like sampling in slow time, if you get my point. So it is little confusing. Now I will talk something about pulse compression. I already show rectangular pulse without any modulation. Autocorrelation function is triangle. Yes. If I will make cross correlation with receiving pulse, it will be in spectrum is sine x divided x since function. So wall energy triangle has very pure very pure resolution because it is triangle. It is really not narrow. You can agree with me. Spectrum of this is since function. It is also clear. And now, what is pulse compression? Pulse compression is that I want same energy which is in a rectangular pulse, put it to another pulse that has much narrow main lobe. Why? Because then I can recognize, then I have better resolution. So this is called pulse compression, and there is example of LFM compression, linear frequency modulation. So the basic motivation is to decouple peak power from range resolution. Classic short rectangular pulse give good resolution, but to reach long range we would need very high power. But I don't have this power, or I can't even make this so high power. So I need reducing, and I will use inner modulation. So with pulse compression, you can transmit long low peak pulse with intra-pulse modulation. So energy will be same and pulse will be long enough. Because how you can in spectrum, if you have since function, it is clear that main lobe is inverse value of pulse length. But I can make 1 nanosecond, 0.1 nanoseconds. You can't do it because it is so short. So pulse compression allows me make longer pulse, but with the same resolution. So it is my motivation. I will skip international mismatch filter. Okay. Which radar signal we use for for radar signals? It is unmodulated signal. Okay, it is rectangular pulse. Then we use linear frequency modulation, LFM. Non-linear frequency modulation, it is NLFM. Frequency keying and phase modulations. So BPSK, MFPSK, QPSK, Barker codes, minimum peak side lobe, pseudo-random sequences, code approximation, P codes, Frank codes, and so many others. Guys, this is just definition what is inside the pulse. And each this signal has own unique properties, generally. Then MTI filtration. MTI filtration, I already told you, it is removing of clutter. So ground clutter suppression is on MTI. Then there is example of MTI filters. There is two targets. if you can recognize, and this is jamming. So it is some chaff jamming. I don't know if you know what is chaff jamming. It is, imagine that you have somebody want to track you, or some missiles goes to your side and want to hit you, and you will see which kind of missile, and you will just send to air cloud of small metallic plates or something like this, and size of this metallic small plates that flow in wind, they have like half of wavelength of this your frequency, and for missile will be like, oh, where is target, because they didn't see you after this clouds. So it is chaff. It is small, it is millions of small metallic, some not plates, it is like aluminium, something like this. If you get my point, it is something like this. This is clutter. There you can see it is after MTD, it is MTI filter. So this is no moving, so it is chaff, probably no wind because there is chaff. This jamming, you can saw it in MTI, after MTI MTD in zero Doppler shift. So it is mean there is no movement of this chaff, so you can see it there. And this is output from MTD filter, and I don't know in which speed, I am sorry, but imagine this is the whole picture. What is target? I don't know. I see everything. I see reflection from chaff, I see reflection from environment, I see some screen, this one. After I check MTI, there I see only static object, what is not movement. Chaff, environment, clear. And after MTD, I see only what is movement. Same source data, different filtration. It is like selection, what do you want to see, generally. And there I have nice picture, this of MTD. Check it, this is MTD filter. There you can see this value. It is minus 23.3 meter per second. So it is negative, it is, these targets go away from you, from radar, or opposite side. And check it, I will do it multiple times. Check the speed, you see different and different and different. Okay, there was speed 0, clutter, environment. Okay, I will do it again. I don't want to make animation because if we need to stop somewhere, so. And this is real data from radar. I can't tell from which one, but it is from radar. Okay, then next steps in radar signal processing is detection. Detection is evaluation of target's presence in a resolution cell. It is target there or it is not there. So it is statistics, you will like it. So it is two like hypotheses. Null hypothesis, noise only hypothesis, target is not present in cell. Alternative hypothesis, H1, target echo and noise is present, because noise is always there. So target, no target. Then type 1 error is that we decide target is present, but it is not true. You understand me? Because, okay, I evaluate due to noise, okay, amplitude was higher in my resolution cell, and I decide, yes, there is target, but it is not true. but of course I don't know it. It is statistics. Then second type of error is that there is target in my cell. Sorry, I decided there is no target, but it is not true. Target is there in my cell. And the detection or detector always need to make this decision of hypothesis. And it is depends, of course, on probability of false alarm and and inversion value 1 minus PD is that I miss target. So it is probability of false alarm because I decide, okay, there is target, but it is not true. And there I tell there is only noise, but it is target. So somebody can tell me, okay, if I don't want miss anything, I will set probability of false alarm very low, because then I will detect almost everything. But you will have so many false detection, if you get my point, because I tell, okay, if threshold will be low, then I tell, okay, it is low. So any noise disturbance, some higher amplitude, something told me there is target, and it is not true. And what's happened? On your screen you will see so many targets, and then it is not true. If I will set opposite, so detectability rate very, how to say, high, then I can miss big target. Why? Because it is I expecting so high amplitude, but unfortunately this is weak target, so low reflection. So we need also with statistic, and this is a little like crystal ball. It is not easy to compute, and of course it is depends on also CFAR, constant false alarm rate, because this CFAR told you what is false alarm rate, what is probability, and it is adaptive. If you see incoming storm with snowing something, your clutter for sure will increase, because it is clear, because there will be more reflection, so you will increase this threshold or decrease and so on. So it is usually adaptive. Okay, I will skip this. Then is extraction. Next one step is extraction of target coordinates. It is consolidation of target information gained from multiple observation. It is through CPI, because I told you we have PRI and we send these pulses. We make sampling, we gather all information from all pulses, and then we need make fitting which target correspond to same, which pulses correspond to same target. It is one big target, it is two small targets, just as fly close to each other, and so on and so on. And in these steps I make determination of target coordinates, and then next step is classification of target, and it is mean classification is determination of targets class. It is fixed wing, helicopter, or it is wind turbines. What is it? And I can recognize from amount of information what I have. Adaptive CFAR, I will integration, it is utilization of more echoes received upon illumination of one target. If I have one illumination, if I have more illumination, I need to put together. There you have approximate values that is used for non-fluctuating and fluctuating targets. So detection probability is 0.9, false alarm rate is 10⁻⁶, for fluctuating is usually 0.n and again 10⁻⁶, so it is just like typical values. Okay, and I talk about classification. Yes. Okay. Sorry for speed up a little, but this rest is not so affect other lectures. Slow, fast time, it is important for us, but after this it is like secondary processing and then tertiary processing, but we will not be affected for next lecture. So I don't know what is time. Okay. Okay. So we are missing tutorial today, but I will start tomorrow not with lecture 3 but with tutorial. Please take your laptop and I will ask if you could send me all participant emails, or I will ask organizers if they can send me a list of emails, and I will send you all material. I will send you link where you can download all these MATLAB files, and tomorrow morning you will receive email, and please take your laptop as possible and we will work all together on this tutorial. Thank you for your attention and that you have patience with 5 hours with me.